So hello everyone, this is Shyam. Today we are going to discuss about a nonlinear system in finite difference equations. So first let me write down. So we are going to discuss finite difference equations, and in finite difference equation we are going to discuss about nonlinear systems, nonlinear equations. Okay. So most of the natural world, most of the phenomena in the natural in the real world, or you can say natural world, are modeled using nonlinear equations. Nonlinear equations. For example, so example, one example is population dynamics. Population dynamics. So this is example from population dynamics. For example, logistic growth. Logistic growth of any single species population. Single species population. For example, rabbit population. Rabbit population. So the given equation, for example, the rabbit population is nt plus 1 equal to rnt 1 minus nt. So where nt is the rabbit population, rabbit population at a given time t, uh, nt plus 1 is a rabbit population at time t plus 1, so it's the next generation, and r is the growth rate. So this is equal to b, the birth rate, minus death rate. So where b is birth rate and d is the, sorry, death rate. So this is one example from population dynamics. So another example I can give. Uh, so this is example of a logistic growth of a single species. Then you can say prey-predator systems. So prey-predator system. Sorry. So this is an example from ecology. So competition between different species in an environment. Another example you can say oscillation, biological oscillators, biological oscillators, biological oscillators. Example: fireflies, neurons inside human brain. Uh, Oscillation of heart. So there are plenty of examples where you can see the underlying equations are nonlinear. So there are many examples. There are plenty of examples. There are plenty of examples where underlying equation equation sorry is of nature is of is a nonlinear equation. Okay, so let us first try to understand what is the form. Okay, so the standard form, the standard form, or you can say general form of a mth order nonlinear equation. Okay, so consider one finite difference equation. Sorry, finite difference nonlinear equation is of the form xn plus 1 equal to f of n xn n minus 1 up to xn minus m. So this is my equation 1, where f is a function and it is not a linear combination of the previous terms like xn up to xn minus m. So example as I given above is the logistic equation. Here you can see. So this is an example of a nonlinear equation. Okay. So this is called a logistic equation. Let me write it down. Logistic equation. So logistic equation. So it was given. It was proposed by Verhulst in I guess 1840. Sorry, 1838. Long back. So now we will. So we'll go to the next page. Uh, okay. So fast order nonlinear equation. Okay. So consider a nonlinear equation x n plus 1 is equal to f of x. So this is equation 2. Okay. So here f is a nonlinear function of xn. Let x bar is the fixed point, fixed point, or you can say equilibrium point of f. That is f of x bar is equal to x bar. This is equation. Sorry, this is equation 3. So what is x bar basically? X bar is the fixed point. So basically, when you say x bar is the fixed point, you have x n plus 1 is equal to xn is equal to x bar. It means at this point, your population will not grow. If x bar is the fixed point, your population will not grow. So it is so that's why it is called stationary solution. So sometimes so this is equation 4. Sometimes x bar is called stationary solution of equation 2. Okay. So graphically what does it mean? So let me draw a figure to understand clearly how it looks geometrically. So okay, so we have this figure now. Okay. Okay. So this is f of x and this is x. Okay. So this is your xn plus 1 xn and this is your xn. Okay. So you draw a line having slope 1, so you can draw something like this. Okay, so this is y is equal to x. So your slope is 45 degree. So you draw a smooth curve like this. So this is my curve. So this is my f. So this is my function f, and this point, basically the point of intersection between the function f and the line y is equal to x, is the fixed point for f. Okay, so let me draw here. So this is the point of intersection here, and you take okay, let me draw something like this. Okay, so this is my, basically this is my x bar, and this point is my x bar comma x bar, because my x bar is f of x bar, because x bar is my fixed point. So this is the geometrical interpretation of this, how stationary solution looks basically. So this is figure 1 in our lecture. So figure 1. So x bar is the fixed point of f. Okay. So the next question is the following. So you have a question. The question is the why we study fixed point in a nonlinear system, or or we can rephrase it, why fixed points or equilibrium points or you can say stationary solutions of a nonlinear system are interesting to investigate. So before answering this question, we need to understand what is called homeostasis. Okay, what is called homeostasis? What is called homeostasis? What is this term basically? What is this homeostasis? Okay, so so this is a definition from Wikipedia, where I can write the definition. Homeostasis is any self-regulating process by which an organism tends to maintain stability. So this is important. This word is important. The stability. This is a very important keyword. Stability while adjusting to conditions that are the best for the survival. If homeostasis is successful, life of that organism continues. If it is unsuccessful, or if it is unsuccess successful, it results in the in a disaster or a death of an organism. Okay. So this is the definition. So homeostasis is any self-regulating process by which an organism tends to maintain the stability while adjusting to the conditions that are the best for the survival. For example, you take the human body temperature. So our body temperature varies between basically 37.6 to 36.3 or 2. So on the daytime, your body temperature will increase and it will touch around 37 point something. And in the night, it will reduce to 36 point something. So it is kind of oscillation. Your body temperature oscillates between these two values. If your body have to work, the body will maintain this temperature inside your body to regulate your day-to-day um, thing inside your body. If your body temperature will rise above 37 or it will go below 36, then there is some problem. If it will go on increasing your body temperature, then there will be a lot of problem and it may cause the death of that person. Okay, so that's why homeostasis is the, let me see one thing. So if you will, okay, so if complete this page, okay, let's go to, if you will look at the book by Professor Lake is it. Let me write down the name of the book. So it's mathematical models in biology by Professor Lee Kissett. I guess she's a professor in University of British Columbia or Alberta. I have to check. So she has written a classic book. It is in classics and applied mathematics. So she has like homeostasis. She has given a definition of homeo homeostasis. Professor Lee Kissett. Lee Kissett. So see what is she saying? She is saying the concept of homeostasis or equilibrium studies is related to the absence of the changes in the system. Okay. So the concept of homeostasis or equilibrium or steady state is the absence of change in any system. Sorry. System. Okay, I will check. So the concept of homeostasis or equilibrium or steady state is the absence of any change in any system. So this is the definition given by Professor Lee Kissett. So if you have a system, for example, the population in your city, the population will not change due to some reason. So this process is called homeostasis. Or if your body temperature will not change, or how to say, so for example, your heart rate is 72 times per minute. If it will not change, so this process is called homeostasis. Okay, then why? Okay, so why these steady state solutions are important? So in some cases, basically, steady state solutions are of intrinsic interest. For example, most living organisms function well in rather narrow ranges of temperature, acidity, or salinity. Okay, so some living organisms functions well in some rather ranges of temperature, acidity, or salinity. Some more highly evolved organisms have developed intricate internal mechanisms for maintaining the body temperature and other factors at their appropriate constant levels. On the other hand, study solutions may seem marginally interested in problem solving dynamic events such as growth, propagation, and reproduction of a population. Nevertheless, it is often true that examining carefully what happens in a steady state, we can better understand the behavior of a system. Of a system. Okay. So I think we have to stop today now. Today, so this is the end of the lecture today. We'll discuss in the next lecture. Okay. Okay, stop sharing and